welcome to the first session of Integration and Fusion. We've got 3 exciting talks for you. Can I just ask, if you're going to ask any questions after the talk, can you please wait for the microphone to come to you and speak into the microphone, say your name and where you're from, because otherwise it won't be picked up on the recording. So, first of all, we have Ran Yu, who's from Leibniz Institute for the Social Sciences, and she's going to be talking about No More, which is a knowledge-based augmentation with structured web markup. So...
Good afternoon, everyone. My name is Ran Yu. I'm from GASIS, and I'm presenting our journal paper published, accepted at Semantic Web Journal on 2017 and published earlier this year. And this work is a collaboration with colleagues from ISWC Research Center and the University of Mannheim. So the name of the paper is No More, Knowledge-Based Augmentation with Structured Web Markup. Maybe there's... I think maybe we need to plug in the USB stick.
Okay, have you got the USB stick?
This one from the room.
Sorry, I have a problem with the... Is that the... It's blank. Have you got this on your laptop? Sorry?
You open it up on the flash drive?
Yeah.
Take it on the hard drive.
Okay. To do that. So how? Let me look at it.
So copy it to the desktop.
Okay.
And then open it from there.
Yeah, it
Okay.
works.
Good.
Okay. So the talk would include in 4 parts. I'll briefly explain the motivation of the work, summarize the related work, and introduce the data source we use and our approach. So start from the knowledge base. The knowledge base in this talk refers to the RDF data sets. For instance, DBpedia as the most frequently used data set by researchers. There are instances of real-world entities in the database, and the instances are identified by the URI as the subject of the triple, and then there are properties and values saved as RDF triples to describe the entity. There are a lot of applications using knowledge base as background data set. For instance, there are semantic search. Google answers entity-centric queries using knowledge graph in the backend. For instance, if I search for Forrest Gump, a summary of the entity will be showed on the search page with a rich representation of the search result. And there are product search and product recommendations, and also question answering systems using knowledge graph. And smart assistants such as Amazon Alexa is also using knowledge graph to answer, to have conversation with users. The current state of the knowledge graph is that there are a lot of open accessible data sets. For instance, as reported by Linked Open Data, there are more than 1,200 data sets and more than 100 billion statements by March 2019. And there are even more. There are also more knowledge graphs preserved by different companies that are accessible through the applications provided by the companies, such as Google Knowledge Graph. So in summary, the knowledge graph has attracted a lot of attention, and it's at a fast-growing scale, and it covers diverse domains. However, it still suffers from the challenge that the knowledge bases are very incomplete at this moment. In particular, there's a large percentage of less popular, also called as long-tail entities and properties that are underrepresented. So on these slides, I'm showing two examples. The one on the left side is the statistics about the entities of type person in freebase. This is from a paper published in 2014. As you can see that among all the person entities, there are 68% of the persons do not have a value for profession. And even for the properties such as place of birth, which everyone's supposed to have, there are 71% of entities doesn't have value for this property. Even for the most frequent entities, the top 100,000 frequent entities, person entities, 13% of persons are missing place of birth. On the right side is a snippet taken from our experiment data set, where we randomly selected 30 movies and 30 books from Wikipedia. And then we get statistics about the top 15 popular properties, see how many of these entities have values for these 15 properties in DBpedia, Freebase, and Wikidata. The space you see between the top of the bar and the 100% are the missing the percentage of entities missing the respective property. And most of these are the gaps that we want to fill in with our approach. But one thing to note is that not every entity is supposed to have all these 15 properties populated. For instance, for the movie entities, there's a property we look at is a word, which is not supposed to be 100% for every entity. But the good thing is that the linked data or the knowledge base is still just a very small fraction of the web. And there are a lot of knowledge buried in the unstructured or semi-structured web data. There are a lot of works has developed approaches for enrich or augment the knowledge base using web data. For instance, there's a line of work using internal data from the knowledge bases, which is mainly inference on existing knowledge for new relations or new types. And there are a lot of work using external data from the web. And for instance, there are work using unstructured web documents like the article, free text article in Wikipedia, or news articles, or general web page and product descriptions from Amazon for populating the knowledge base. And there are work using semi-structured web data, for instance, using web tables or web markup as what we do in our work. Web markup are the structured entity informations embedded into web pages using standards such as macro formats, RDFA, or macrodata. The right side of the slide is an example of IMDb page of the movie Forrest Gump. If you look at the source code of the page, you can see that there are some entity information embedded in the web page using macrodata standard. And for instance, you can see from the source code that Tom Hanks is the value of the property name, which is a fact about entity of type person, and this person is the actor of the movie Forrest Gump. So Web Data Commons dataset is a dataset that extracted from the web markup of web pages in the Common Crawl. And for the Web Data Commons dataset extracted from 2018 November version of Common Crawl, they found that more than 37% of web pages have this kind of web markup, which covers more than 29% of pay-level domains and constitute of more than 31 billions of RDF quads. So this Web Data Commons dataset is of very large scale. It contains up-to-date information. It has information for long-tail entities and properties. And it already used some kind of ontologies, which are most frequently used ontology is schema.org. And it has semantic annotations and relations and easier to pass than unstructured web content. However, there are a lot of disadvantages of this dataset as well. For instance, there are a lot of common errors, like raw namespace or the website manager might use undefined types and properties just because this vocabulary makes sense, but didn't really look up in the ontology definitions. And most of the instances are unlinked. For instance, the entity descriptions for the same entity are isolated with each other. For instance, in the Web Data Commons dataset, there are more than 10,000 instances for if you search for iPhone 6, but all these nodes are isolated. You don't know that they are coreference entities. And this also results in very high redundancy of the data. And there are a lot of semantically misused vocabularies. So it comes to our approach of resolving these challenges. We developed an approach with 3 steps. Where first we clean the data to fix the issues such as common errors, and then we run entity matching step to find the coreferences for the entity that we want to augment. And in the end, we fuse all these matched entity coreference entity descriptions to find the new and the correct facts for this entity that we want to augment. So the first step, entity matching, we use BM25 as a blocking step to run a fuzzy match for the name of the entity description in WDC dataset and the query entity. And then we run a pairwise comparison, which is a supervised classification approach. We consider each property, the properties as feature space, because that we think different properties contribute different weights when you decide if these 2 entity descriptions are the same for the same entity or not. For instance, the author might have higher weight than publisher when you decide if 2 books are the same book or not. And with this similarity vector, we run a supervised classification to classify whether or not these entities are coreference. And after we get all the matched entity descriptions, we extract features from different dimensions. For instance, we consider the similarity. We consider the quality of the source and other dimensions to extract features, and apply another supervised classification to classify the facts from all these matched entity descriptions to decide whether or not this is a correct fact or it's a false fact. At this step, we remove all the wrong facts. For instance, Tom Cruise is not an actor of Forrest Gump, and then we remove this fact from the pool. And the next step, we ensure the novelty of the fact that we found, which basically means the fact we extracted should not be redundant among themselves and also not redundant with respect to the corresponding knowledge base we want to augment. For this approach, we have to run an experiment using Web Data Commons 14 dataset. We create ground truths on the 30 movies and books randomly selected from Wikipedia. And we augment DBpedia, Freebase, and Wikidata. The properties are as shown, the 15 top populated properties, and we manually mapped the different ontologies across KBs to schema.org vocabularies. So I'll briefly show some of the evaluation results. We use precision recall F1 to evaluate whether or not the facts we selected are correct. So this is evaluation of the correctness step. And we see that the F1 measure outperforms all baselines, which we have one baseline which focuses on the precision and the quality of the facts and the source of the facts, and another approach focuses on the novelty of the facts. So our approach outperforms both baselines, and with especially the recall is much higher than the other approaches. We also evaluate the novelty of the facts that we recalled from the dataset. And the novelty we have over 90% novelty for the facts that we extracted for augmenting the KB. And we're also able to recall over 90% of novel facts from all the matched entity descriptions. And there's a slight trade-off between novelty and recall if we set a threshold into different values. But this threshold is for filtering out the duplicate fact based on the similarity metric, which does not influence values of numbers. Values has type of numbers or date and date and time. That's why it's not it doesn't have a very strong influence on the result. And we notice that we can get for average 40% of movies without genre has been augmented with at least one genres. And there are, for other properties, we also have increased coverage in the knowledge base after augmenting using web markup data. So there are more evaluation results in the paper, and we also evaluate the potential of this approach, and we notice that we can find a lot of new facts which the properties has already been used by DBpedia, and we can also find new facts of long-tail properties that are not used by DBpedia yet. And here is a brief example of a book that we try to populate, and we see that we can recall a lot of new facts from which are originally that do not exist in DBpedia. And briefly, the conclusion is that we could find facts for augment machine-readable knowledge bases from the web, but for some fact we need to consider to be more considerate on how to add it to the knowledge bases. For instance, if we want to add add information about different versions of books in the same page, or we want to consider as different entities, or some facts are only temporarily correct if we want to have it in the database or not. Thanks.
Okay, thank you very much. Really interesting. So, are there any questions? Yes. So there's just a microphone. Is there a microphone anywhere? No. Okay, I guess you can't use the microphone then.
Today there's, it's often the case that people put false information on the web in text, and I can imagine that if this technique is used a lot, then the next step they'll do is to try to embed semantic markup in there for the false information, which could then prevent a risk for this technique.
Yeah, that's a good point. It's actually true that there are already a lot of false information in the web markup data set, but we try to add this kind of quality control into the features in order to filter out the facts from the not so authorized resource. But yeah, there are still some false information in the result, and we need to continue working on that.
Are there any other questions? So I have a question about, do you do any analysis of which facts you want to find out? So you were saying that there are some attributes that you wouldn't expect everything to have, and then there's presumably some attributes that are less interesting or less central to what it's about. Do you do any analysis of which ones you should be prioritizing filling in? Which facts are the important missing ones or not?
Yeah, I guess which properties or facts are important would more or less depend on the applications. Mm-hmm. In our case, we developed the approach for general purpose, so we assume that we could find the correct and the novel facts. And if the fact is important for a specific user, it would be more dependent on the specific application that this knowledge base aims to be used for.
Okay. I think that would be an interesting problem if you look at more specific domains about
how you
absolutely. Can then focus on the key issues.
Yeah.
Is there another question? Okay, let's thank the speaker again. Thank you.
Thank you.
Yep.
So our next speaker is going to be Damien Grouse from Adapt Centre in Dublin. I think that's right.
Exact. This is exact.
And So he's going to be talking about triple storage for random access version querying of RDF archives.
Exactly. Okay. Yeah, thanks for the introduction. So I'm Damien, the second in the list, presenting today Squerall as a resource. So basically I'm going to speak and explain what mainly Mohamed Najib Mami has done during his PhD time at Fraunhofer, which is a virtual ontology-based access tool to reach heterogeneous and large data sources. We call that Squerall. So first, a bit of context. As we have seen already, for some of you who were there yesterday during the nice tutorial of Juan, who will be like the next speaker, we have like 40 years of relational data management behind us, and for the last 10 to 15 years, like new paradigms for data management have been, created and fostered, like new models, non-relational and NoSQL data, structured file formats, new SQL, and so on. And there are also new capabilities, like scalable storage and querying. With those new context and paradigms come new challenges, the 5 classic V's of big data, and we were facing some challenges, some classical challenges that you might have faced too. Typically, there are some data lakes, the new term which has been coined recently, of large and heterogeneous data sources, dispersed into data silos and stored usually in non-interoperable systems. Then there are also the centralized traditional data management system that have been reaching their limits. And in addition, there are more and more heterogeneous data sources that are created or set up, having various data formats, several query syntax or query languages associated with, and thus it's difficult to provide access or to wrap all of them. And what we wanted, and what Mohamed has done in his PhD, is to try to propose a tool which would be able and easy to use, which would be able to help users to directly touch those kind of various sources. So the idea beneath is the following: having a semantic technology for virtual data integration, which would be based on ontology in terms to create a cross data source schema. And so relying on mappings, mainly RML mappings, and also using Sparkle as a unified query language. So this is basically the solution of in a nutshell that we are proposing, and we have called that Squerall for Sparkle Query at All Time, which is Squerall a semantic data lake, as we are trying to coin this. So it's a virtual semantic-based data integration system, directly querying original data. I mean, no prior transformation needed. So the idea is that Squerall, we will see that a bit later, but Squerall is directly touching and querying or subquerying the various sources. It allows scalable cross-source query execution, enable query time transformation thanks to the function ontology that we'll describe roughly later, which has already been existing for 2 years now. And the idea is not to reinvent yet again the wheel, and to be able to use existing engine connectors, wrappers or connectors that are already existing and that have already been developed by the community. And by doing that, we are trying to keep Squerall extensible to new sources that might arise after. So briefly, the architecture is the following. So you have your data lake with various data sources having different formats and structure, a Sparkle query, and then first of all, following a classic approach, we are like decomposing the query into what we call star-shaped subquery. I will describe really roughly later how they are looking. And then thanks to a set of mapping that has to be also provided by the user, we can reach the relevant data sources to query based on the query that we have. then the data wrappers, thanks to also other configuration that the user can give, are in charge of wrapping everything. And from now on, so all of that was kind of external. I mean, those data lake structure is external to Squerall. And from here, it's based on Apache Spark. So there is a distributed query processor on top of everything, which is in charge actually of transforming a bit the data to make some alignment so that we can join together the sources and then join these new results in order to obtain the final results. So let's have a really quick look at some more details on the query execution flow. So typically you have your query here, decomposed like so. And what we are doing is that we are decomposing the clauses in terms of stars, as we call stars, which means that we are looking at the common subject variable. So we are building those kind of small stars molecules from the clauses. And then we are using the source detection with the mapping to know which kind of sub data sources we want to reach. This is now the creation of the parsed definition. If you remember the architecture that I've just presented before, we obtain our new sub-results. And then now we are looking at the various filters that might also be in the query in order to refine those sub-results on the fly. So there is kind of a push, the classic push-down filter approach is respected here and implemented. And now comes the real joining part here, that I will detail after. And at the very end, some kind of aggregation function might be also applied just before like rendering the results. So if I retake the same kind of clauses, this is exactly what's happening. So the algorithm, I mean, the Squerall is searching for the common variables to join on, following this kind of classical approach. So I'm going fast on that because it's quite common and classic. And then we are implemented this kind of left join policy right there, which is an incremental join. So this is the default approach, and that I wanted to present here. But Squerall also come with roughly some additional policy of aggregation and of joining, such as slight one based on statistics on the sub-results in order to limitate these intermediate results that we might have, for instance, here and here, like reordering a bit what might happen. In a nutshell, but I suppose that you are more or less all familiar here with this kind of mapping declaration based on RML here. So we are using it. The Squerall can be fed. I mean, should be fed by this mapping declaration. But what is also interesting here is those function mappings that look like so. Sorry. So the idea here is to be able to align sometimes some sources that are not exactly looking the same. So typically, you could have, I don't know, maybe on MongoDB, some identifier for some field, and you want to join with a Couchbase column, maybe. And sometimes you have a problem because what you have in the field, they are representing exactly the same entity, but they are not exactly written the same. For instance, you can have like some identifiers that would be offset from in the second source rather than in the first one. And this kind of function mapping allows us to align perfectly together the various sources before the join. So it enables new joins. So let's have briefly some idea of how the implementation is done. So basically, Squerall relies on Apache Spark or Presto for really the query engine and how to join then after the sub-results. So it's up to the user to decide or to select between Spark and Presto. RML is used for the mapping as a mapping language, and the function ontology, FNO, for the declaring transformation, Gina for query analysis and mapping everything, and all of that is written and completely open source in Scala. At the moment, the data sources that are supported are MongoDB, Cassandra, Parquet, CSV, some JDBC, like MySQL, Couchbase, and Elasticsearch. And we also provide a user interface. Here is a slight word on how extensible is our architecture. So the idea is that we also allow the user or to contribute directly and to also write his own or her own mappers to extend the set of reachable data sources. I have here, like in a nutshell, some performance evaluation, but maybe I will be quick on that. So the idea is that to evaluate that, we have slightly modified a bit the classic Berlin benchmark. And here are some kind of performances based on the benchmark that we are using. So here you can have a look at the phase decomposition with Spark or with Presto for the same benchmark. Basically, without surprise, the time which is the phase the more consuming is the query execution, not the relevant data source selection nor the query analysis. Here are the results on other scales, so 1.7 million tuples or 5 million tuples. You can see that the shape, the way it is distributed, remain the same for the engine. And here are some additional, that you can see in the paper, some additional results based on some specific metrics that we have also looked at. So we paid a bit attention to the CPU consumption or the memory or the data which is sent across the network. And we can see, what we discovered, which was not really a surprise neither, is that the pikes correspond to the disk read and the shuffle done either by Spark or by Presto. Here are some rough and basic snapshots of the query interface that we have. So the idea is also to help people to create the mappings or also to create directly their SPARQL query. So we have a demo then after this afternoon. So if you want to join and see a bit more about those interfaces, you are definitely welcome. And I will finish and conclude by this sustainability, availability, and adoption plans that we have as a resource. So far, everything is already open on GitHub and runnable via some Docker file. We paid attention to be completely reproducible on the experiments. So we have the evaluation environment, which is completely available on Docker. So you can just pull everything and then make it running on your own laptop and have a look at what would be the performances. In addition to that, we also successfully integrated Squerall, some parts of Squerall directly into the Sensa stack, which will have also a demo made by Klaus Stedler this afternoon. So you can drop by the Sensa also presentation. And it will be sustained by several European mainly projects until 2022. And at the moment, it has been internally evaluated by a large industrial German company for a specific use case. And as future work, we are currently working on extending the SPARQL fragment that we are supporting at the moment, and also to have additional join orders policies, for instance, to improve the performances. So thank you very much for your attention.
Just take questions without microphones.
So many of these data sources support different features. So for example, Elasticsearch has an inverted index text search. Do you plan to support special things in SPARQL that exploit these kind of specific indexes or structures?
At the moment, no. But this is a really good question, which often occurs, like when we are presenting Squerall. The thing is that we are processing the other way around. We already have SPARQL, a fragment of the SPARQL query language that we are more or less covering properly. And then at the decomposition phase, when we are basically the query is split into pieces, and the Sparkle query is split into pieces, and then some of those pieces are then translated into the ad hoc or the dedicated query language to retrieve the information like so. And the thing is that, unfortunately, we are not, using, we are limited. There is kind of a bottleneck there. We are limited by the features that we have in Sparkle in terms of the translation. So in terms of semantic power, it's a bit limited like so. Unfortunately, for instance, with Elasticsearch, we cannot, benefit from those kind of really specific features, additional features at the moment.
Yeah, so one of the well-known issues about doing this ontology-based reactions are the optimizations, right? So the two main optimizations that we looked into, I hate to talk about my own work, but it was self-join elimination, or at least semantic optimizations, that either you have to implement them outside the box or the existing databases implement them. So what do you do? Are you doing a bunch of self-joins, or are you doing self-join elimination? When you push down, you eliminate the stuff that doesn't return results?
Actually, what Squerall is doing exactly at the moment is that it's how to reduce a bit let me sum up. The idea is that we are starting a bit the idea that we had at the beginning is that we had the federated query engine paradigm that is existing in Sparkle already, and then we instead of querying only RDF dataset, we wanted to query other data sources. So it's kind of the same general architecture as you can find on the federated query engine. And at the beginning also we wanted, so what we are doing at the moment is that, plus pushing down some filters. And we wanted also maybe to have the possibilities of also pushing down directly some join to make some data sources that are say external already self-joining some intermediate result to then obtain them.
So then the results are really, not only don't you have ideal join ordering, but then you're doing a bunch of self-joins. So these results that you're showing there are they're bad because obviously you're not doing, you're doing the optimal join ordering and you have a bunch of extra joins. So I really can't make use of those results you're telling me doesn't tell me anything. In my opinion.
Okay.
How are you handling, because in example you put there is innocent, how are you handling optional factors?
So at the moment we are working on this on the extension toward optional. So we did it, this is not handled at the moment. Yeah. The Sparkle query fragment, which is supported, is the classic BGP plus plus the filters and some solution modifiers, typically order by. Yeah. Yes. Yes, that's it. Yeah, plus ordering as a solution modifier at the end. Yeah. Yeah.
So we've got time for one last question.
What do you mean? No. We have the select, distinct, and then the projection. I can't hear you. Yeah.
Is there one more quick question? Okay, thank you very
much. Thank you.
Oh, is it?
There we go.
Okay, so the final talk in this session is from Juan Sakada, who's already given a very interesting keynote talk at the Ontology Matching Workshop. This is one of the spotlight papers, so it should stimulate some interesting discussion. So, Juan.
Thank you very much. Thank you. It's a true honor to have this paper as a spotlight. It's a Best Paper in Use nomination. I got T-shirts, so ask questions. You get T-shirts. So how do we get from... Oh, sorry, this is an in use, just to get it clarified. So how do we get from enterprise relational databases, right, really complicated real-world databases, to what we're calling these enterprise knowledge graphs, things that are very well understood, well-defined schemas, but also taking into account the people in our organization. So that's what I'm going to be talking about for the next 14 and a half minutes. So the takeaway is the following, right? The question is, how do we get from these enterprise relational databases to these enterprise knowledge graphs? And our answer is, we need to have methodologies. And that's what we're presenting here. We're presenting a novel pay-as-you-go methodology that is really combining the engineering of ontologies also with mappings. And I think two particular insights is in this pay-as-you-go iterative approach is that we want to focus on answering business questions, because that helps us determine what success looks like. And what we've observed and what we've learned in real practice is that we can actually achieve this success without boiling the ocean, meaning without having to create an ontology of so much stuff and spend so much time and money and then create all these mappings. So even though if you were in my tutorial yesterday, I said we should not spend time defining what a knowledge graph is, well, in the real world, when I put my sales hat on, I got to talk what a knowledge graph is. So this is my informal, inclusive, non-pedantic, non-scientific definition, which I can say because this is an in-use paper, is if I need to integrate data and I need to have concepts and relationships as first-class citizens, that means I am linking meaning and data together in the form of a graph. And that's what I'm calling a knowledge graph. Note that I'm not saying anything about RDF or ontologies or whatever. And I really like this quote from Brad Beebe, who is a program manager of Amazon Neptune. He says, imagine linking things that were never connected before within your organization. That's what you can do with the knowledge graph. So in the paper, we discuss a case study, which was one of Capcenta's first customers, which, oh, by the way, this was work that we did while we had my company Capcenta. Now Capcenta is part of Data.World. So in the early couple of years ago, one of our first customers, we had this e-commerce company, and the background was the following, right? They had already invested a lot of time, a lot of money in creating this enterprise data warehouse, but for many, many reasons, this data warehouse wasn't being used. Why? Because the business users were skeptical of the data that was part in that data warehouse that was feeding these reports. Therefore, the data warehouse wasn't being used. And that's kind of a reason why data warehouses fail. So what happened was that the business users were going directly to the sources and talking directly to the IT folks, and this was becoming the bottleneck. So the challenge there is because the business users talking to IT all the time, they were completely bottlenecked. And then you had this big friction between business users and the IT folks without, what do you mean by this? What's the terminology? So much time was being wasted to be able to understand what this is. There's all this tribal knowledge embedded in Excel, in wikis, and documentations, in emails, and macros inside of Excel documents, and Access databases. The business users would get different answers for the same question. And they wanted to go use a fancy new business intelligence tool like Tableau. And how was that going to be successful if I can't even understand my underlying database? So what the customer really needed is that they wanted to have a trusted view of their data, of their multiple relational databases, of their multiple enterprise databases, right? And they wanted their BI tools like Tableau to consume this trusted data. And we are now in this era calling data-driven organizations and self-service analytics. Well, they didn't want just a handful of people running their business reports. They wanted a large number of all types of data analysts, business users being able to do this, to be able to ask their own questions. And they didn't want to go down the same route of spending 6 months and $1 million before I can start getting any data out. So they really wanted to have an agile approach. And what happened is that the company was really tired, and they were very visionary, and they realized many years ago that there's this stuff called the semantic web knowledge graphs. Let's look into that. And they were willing to invest time and money for it. So we come in, and I was now encountering myself in this real world, coming from academia, from science, and knowing all this theory that we have all worked on, and let's go implement it. So out of the many challenges, I'm going to highlight two. One is ontology engineering, right? We have all these very sophisticated ontology engineering methodologies. Again, if you came to my tutorial yesterday, we talked about all this work in the 90s that people have been doing about ontology engineering based on competency questions, test-driven development, ontology design patterns, reuse, and so forth. All these things are out here, but it is really hard to go and take this and implement this with folks who are not versed in the semantic technologies. Then the other thing is that these methodologies to create ontologies, they're focused on the ontology, and populating the ontology, putting the data, is an afterthought. It is not truly part of the core of the methodology. And then even though there's numerous upper-level ontologies, like good relations with people that has come out of this community, FIBO, GIST, schema.org, it's out there, but it's, again, really, really hard to have non-semantic aware folks to be able to go look at this and be able to use them. And also what happens is that they're sometimes extremely high level. That's like, okay, this is interesting, but I don't know how I can actually use this. At an abstract philosophical level, it makes sense, but I want to ground this to my actual problem. I don't know how to do it. And then you have this gap, and you end up doing your own thing again. So that's the ontology engineering challenge. The other one is the mapping engineering challenge. And I think this is one that we really, in this community, have not been paying attention to in the real world. We have this 14, 15 years of the ontology matching workshop going on, and what I've done is, at that time, when we started, we took all this existing work, all the open source ontology matching techniques, because we thought we can take a source schema of a database and convert it into ontology, and you had your target ontology, it would create all these matchings, and they would work. It doesn't work in practice, right? So that really didn't work in practice. Why? First of all, these one-to-one correspondences are extremely rare. Oh, my source I have F name, and my target I have first name. Well, yeah, that's kind of obvious, but the majority of those mappings are not like that. Why? Because you have a bunch of tables called master order, order P, order P, or you have databases like in SAP, they're in German or stuff. Like, how does this actually work? I don't know. My target has a concept called order. What is this supposed to be in the source when I got 15, 20 tables to have the word order in them? Or especially, database systems are application-centric, so they're been modeled to represent a particular the application. So I see columns called segment 1, segment 2, segment 99. What the heck does that mean? And when you look at the values underneath, it's 1, 2, A, B. I have no idea. Now, we're all in this era of machine learning, but I'm postulating that I don't think we will ever automate this problem. Why? Because we never will have enough data to do it. We will never have enough metadata, schema data to go do this. We have a lot of data to go do record linking and stuff. We've had amazing advances on that. But we'll never have enough schemas to be able to go do this. So, the pay-as-you-go methodology. So the first thing we do is we've divided it in 3 phases, and the first phase is what we call the knowledge capture phase. And we start with the business question. So we tell the people, give us a set of business questions that you want to go answer, and literally we'll start with question number 1. And we go through these 3 steps, and we tell people, let's go analyze the as-is process. How are you trying to solve this problem today, if at all? And you try to collect as much documentation as you can about this. You realize that they're running a bunch of SQL queries, and then there are some spreadsheets that people go do something. Or just figure out how they're trying to answer this question today. And then we're going to develop something which is called a knowledge report. And in this process, you're really trying to identify what are the particular concepts, the attributes, the relationships. In other words, an ontology that models that particular question. And then you're trying to find the particular mappings for that particular small ontology. Then we go into an implementation phase, where we actually are going to go in and implement the ontology, implement the mappings, go test our queries that are going to go generate our data, and actually do data validation. This is a crucial step that we forget. How do we know if I have nulls in my database? What is that null supposed to mean? What if my data has duplicates? For some reason, I'm not supposed to have duplicates. What if I model that some relationship is 1-to-1, but in my data it's actually 1-to-many? What do? You have to go validate the data. These are steps that we're not taking into account. And then the result of this is going to be a small knowledge graph that is the data to represent the question that you're answering. And with this, you can now go into this self-service mode and say, you know what, you got the data and you can able to go answer the question because this is very small. And if you are able to answer the question, success. That's how we know we finished the cycle. And at every step, if you are not, so literally what we do is that we have like a board meeting. We go in and we look at all the deliverables, and if everybody's happy with this, we tell them you can continue. Otherwise, you go back. So once you go through this step, you know that you've successful because you've answered the question. You go to now, let's go to the next question. And you say, well, can I answer this next question with the data that I have? Yes? You're done. Go to the next question. If you can't, you say, okay, what's missing? Oh, I should extend this with a new concept or a new attribute. And you go through the process little by little, again. And you keep doing this in a pay-as-you-go. What we've observed is that the communication between the IT folks, who are the ones who manage the data, gets much more kind of comfortable and fluid. So who are the actors involved? The data engineer, which is the role that manages access to data, the business user or the data scientist too, and then I'm also talking about the knowledge scientist. The knowledge scientist is this knowledge engineering 2.0, which you may be hearing me talk about already several times this week. It's the person who, for example, will talk to the business user and understands the business questions, recognizes what are the concepts and the terminology we're talking about. We'll work with the data engineer and we'll be able to figure out the SQL queries, the code to be able to go get that data and access to data. It's the person who can manage disagreements. If people are going off in different areas, we say, stop. Is this discussion helping us to answer the business question? No? Okay. We're not going to have the discussion. Let's continue. The knowledge report, which is managed by the knowledge scientist, is something that is a deliverable that everybody can understand. And again, as you know that I'm a big fan of history, a lot of the stuff that we did is built on the methodology, the famous methodology, and this knowledge report mimics this intermediate representations, these IRs that comes up in the methodology. So to give a little bit of detail, if we say, for example, what is an order? An order, people can use the same word to mean three different things, but after discussions, you realize an order is if it has been shipped or you have account receivables. What does this mean in the data? It means this query. And note that it says 2 and 3. Yeah, you have to really go talk to people to go figure that out. What is the net sales of an order? The net sales of an order in finance is the gross minus the taxes minus the discounts. But for this organization, that's the definition of a net sales of an order, and that's the SQL query. This is the mapping that represents that. Right? How the heck are we ever going to identify this automatically? If not even the humans will agree. Interested in the details? Please read the paper. So at a high level, you want to be able to take your ontology, you have the mappings, you have a Sparkle query that represents the data that the end user can look. Now they have a tabular result that they can go do. And actually, if you cache or you save this in a database, you can write that simple query and it's well documented. Imagine you didn't have this. Imagine you don't have this well-defined, governed semantics. That's the SQL query you have to go run for that same exact data. This is the value of putting semantics on top. This is the value of ontology-based data access. Sorry. So all these tools are out there. It's just how do we put this in practice? So for the result you did for the e-commerce company, in this first iteration, they wanted to see if this stuff worked, and they said, look, here's this existing daily sales report that we want to go and replicate. It took 2 months initially to get started. I was the knowledge scientist. And there was this gigantic SQL query that was around 10 pages long. That was our input that we started to analyze. So they were really surprised with all the hidden knowledge inside of that report. So this is a little bit of how the ontology grew. And this is almost a one-to-one correspondence between the concepts and the attributes with mappings. Every single thing in the ontology has a mapping to it and has a reason for existence. So in the first 7 months, we started to grow with the concepts. For that month 8 to 22, we were involved, and basically the amount of concepts were flat. We didn't add more concepts. We were adding a bunch of attributes. After 22 months, Capcenta was not involved with the customer, and they were doing this on their own, and look how fast they grew. Every single thing was just a bunch of more reports that they were able to respond. So a couple lessons learned. I'm going to take a couple more minutes. Right? So lessons learned. The knowledge scientist is crucial. The success of this approach depends on having a good knowledge scientist. And we can talk about how do we find them and stuff like that. There's a snowball effect. You start small, but once people start seeing the data, they get excited and they want to get more questions involved, and then the data starts snowballing little by little. This was a manual process, I will agree. There's all this amount of iterations, right? But what we did observe is that once the methodology was understood, we started to iterate faster. People have asked us, how do you do maintenance and evolutions, right? What if the schema updates outside of the methodology? What happens if these changes are non-monotonic? Great question. I don't know. So hopefully these are now, the first 3 things are more business lessons learned. The following ones are more scientific questions. I'm hopefully putting stuff in your head because we need to do, I think there's science in here. Evaluations. How do we evaluate these methodologies? I'm presenting a case study that had 33 iterations over 3 years. Is that good? Is that bad? I don't know, right? Well, from an in-use perspective, is we got paid, and I think money was a way to demonstrate success there. But honestly, from a scientific perspective, how do we evaluate these methodologies? I think we need to have critical, really rigorous methodologies for this. What's the expressivity? What type of expressive ontologies can I do with this methodology? This is something what I call RDFS plus minus. We didn't even have subproperties. We had hierarchies but no subproperties. Is that good? Is that bad? I don't know. How can we extend this methodology to do more expressive ontologies? Tools. We need to have better tools. And tools that can work for non-semantic people and that they can be worked in conjunction with a methodology. That's kind of why we created Grapho, our visual collaborative real-time ontology editor. What can be automated? I told you this was a very manual process, but now that we've broken down this problem in different segments, I can now focus and realize, can I automate this part? So we're now working actively with how do we do data set search and recommendations. We're trying to understand what do nulls mean and how to recommend or be able to identify if a null is important or not. Combining data quality but also with the mappings. We have a lot of query logs. We want to be able to analyze and see what we can learn from this. And then from those query logs, I want to be able to identify candidate mappings. If you're very interested, we have a lot of research projects working on this stuff. So I've talked about the methodology. There is this role of the knowledge scientist. In my previous industry talk this morning, I talked about the data, the hybrid data cloud. My takeaway I want you to think about is human versus machine in the loop. We talk about human in the loop all the time. What about machine in the loop? So, to conclude, you can cite this paper for the following. If you want to say in your paper, a methodology combines ontology and mapping engineering, that's a way you can cite this paper. This paper provides anecdotal evidence that a non-semantic team can maintain an enterprise knowledge graph. You can cite us because if we have stated that you can focus on answering business questions iteratively to avoid boiling the ocean. And we can cite if you want to say that the role of the knowledge scientist is crucial to create enterprise knowledge graphs. Are you interested? Please find me. Dave is in the back also. We're looking for research partners and interns too. Thank you very much.
Thank you. We're running slightly behind, but if people can wait a few minutes for a cup of tea, then we can have a few quick questions. So does anybody have a question? Yeah. There's a microphone coming this time.
So my question is about the bootstrapping phase, basically the initial phase. How did you decide about what are the subsets of questions that you will start with? Okay.
Great question. So what we told our customers is give us questions that you are able to answer today, but they take too long to answer. So literally it's I got to go talk to this person, I got to get their queries, they weren't here today, I get it tomorrow, I got to run this stuff, it takes me 2-3 days to go answer it. I would love to get that answer every day whenever I want, number one. Number two is I am answering a question and I get multiple answers for the same question depending on who I ask. Those are the two candidate kind of scenarios. That's how we start off.
Okay, thank you.
Do we have a couple more questions here? No? Yes?
Thanks, Juan, for the talk. Raphael Transi from Eurecom. Just a quick question. In the 33 iterations, how often, if that happens, people have to come back in time and revisit some choices they made and had to reassess past queries they have, business questions they have been able to answer? So was it, I guess, back to your monotonic questions?
Very good. I do not have the number of those that happened, but I know it was very, very low, like literally a handful. And I think why that happened is, one, it was pure luck. That was one reason. It could have been pure luck. I would argue that because we were so rigorous on, we are not pushing this into production until we have other people looking at this, and we were really, really rigorous on every step, we won't be able to continue. I think people, that really had that barrier, and that's how we avoided that.
Yep. So one question here about, it's a little bit tangential to your presentation. It's about the data world context for this work. So I was checking the webpage for the project, and you allow all these integrations with file picker API, cloud middle layers like Box, S3, and so on. So is the point of this pay-as-you-go model that people will use OAuth 2 to create these aggregated file picker API backend systems? Is that the point?
I would say it's the vision. That's the vision. How will we get there? We will find out. But we can talk more offline about that.
Well, I'm just wondering how you handle, you said we can have legacy databases with plenty of tables, columns, etc. So there is a big issue in terms of the mappings. So in a realistic way, do you have any kind of support to do those kind of things?
So we have tools to create the mapping. So I actually have published it here. So our system was called UltraWrap. We had UltraWrap Mapper, which is our mapping tool. Actually, all those things are now being incorporated inside of Grapho. Actually, we're pushing that feature in a couple of weeks. So yeah, we can talk more offline. I can show you about this stuff.
Okay, there's another question over here.
Yeah. Have you used the methodology on data.world, and what does your knowledge graph looks like?
I don't have a demo, but I have a booth. Come to the data.world booth, and I'll show you actually the real-world ontology for this. There is 150 nodes, around 700 attributes. You can just take a look, and you can see it, and you can see it in Grapho. You can see a cool way of visualizing it.
Okay, does anybody else want a chance for free t-shirts? Yes, over
We
here.
gotta ask questions. Come and ask me questions in the booth, and I'll give out t-shirts.
Okay, so let's just make this the last question then, and then plenty of opportunities throughout the rest of the conference to ask questions.
So Juan, in the initial phase, essentially your team accompanies the non-semantic team to do the enterprise knowledge graph thing, right? How do you recognize that this non-semantic team is now able to do that, like continue it without you?
So the evidence I provide is that last part, that the yellow spike, we were not involved.
No, my point is that in the initial phase, you have these 33 iterations, right?
Yeah, the initial 2 months when we started out, right. Literally, I was coming in, I had no idea about this domain, right? So it didn't take 2 months every day for 2 months, right? That's the amount of time kind of getting up to speed, and after that, you kind of start learning. And a lot of these things is also dependent on if people were, there's flat level because people are on vacation, right?
Okay, thank you very much.